there's actually a second part of the fundamental theorem of calculus, and that part involves looking at functions of the form g of x equals the integral from a to x of f of t dt. And one thing I want to point out is the importance about what the variable is here. So this is a function of the upper limit of integration. So in this video, I just want to spend just a brief amount of time looking at functions of this type to make sure that we get familiar with how that function is changing as we change that upper limit of integration. So let's go back to black here. So to begin with, consider the function g of x that I'll define to be the integral from 1 to x of square root of 1 plus t to the fourth dt. Now it's important here to notice that x is, as I noted before, the upper limit of integration, and consequently we have a different variable that is our integration variable, t. Sometimes they refer to that as a dummy variable, so that should play a different role entirely. So one thing I can do to think about this function is we can talk about what is g of 1. So I'll point out that this is an example of a function or an integrand where it is not obvious looking at that what an antiderivative would be. So in general, you could imagine that evaluating this integral or finding, say, g of 5 or other things that would be very complicated. But it turns out that it's not too hard to find g of 1. G of 1 is what we get when we replace x with 1. And that leaves us with the integral from 1 to 1. And we saw in our properties of the definite integral that anytime you evaluate from one limit of integration to itself, you get 0. Effectively, that's asking us for the area of a line. So we can find that exactly, and I'll generalize that to say that if ever you plug in the x value that is equal to the constant lit of integration in the lower bound there, then we can always evaluate g to be 0. But like I said before, other values to plug in here would be complicated because that would require us to actually integrate that function. So we're not going to focus on that, but the question is, what is the geometric interpretation of this function g of x? So g of x is going to look something like the following. So importantly, I am thinking about here, this is the graph of f of t. So the square root of 1 plus t to the fourth. And this is my t-axis. So if we want to interpret g of x, I need to identify 1 on the t-axis. And we can think about that if x were, say, here, then g of x should give me the area under the curve f from t equals, in this case, 1 up to the value x. So that area is really how we're interpreting g of x here. So when I think about the value of x varying, I'm thinking about moving that vertical line that I have above x and then seeing how that affects the area in question. So I'll just point out that g of x is the area under root 1 plus t to the fourth between t equals 1 and t equals x. So a couple things we could look at here. G of x is going to be positive when I plug in an x value that's greater than 1. So if we think about y, notice that the integrand is positive, so our heights are positive, And if I plug in something to the right of 1, then we're going to have a positive delta x as well. Now, if we instead plug in x values smaller than 1, turns out that this will be negative. So it's still true that g of x, that f of t is positive everywhere. So the integrand is positive. We have positive heights. But if you integrate from, say, 1 to 1/2, we know that that's the negative of the integral from 1/2 to 1 from our properties. So that's where that minus sign comes from. Effectively, it's like we have a negative width. And of course, the function evaluates to exactly 0 when we plug in 1. That's what we looked up before. And so I'll just do one more example here that will kind of start to give us an idea of what the second part looks at. So here, I want to start with a function, so consider the graph of the function f of t equals 2 minus t from t less than or equal to 3 and t minus 4 for t strictly greater than 3. And once we do that, we want to sketch a graph of the function that is the integral from 0 to x of f of t. And again, let's just refer to this as g of x. So to start with, let's focus on graphing f of t. So we are going to be looking at a piecewise defined function. And we can think about here that looking at those pieces, we're going to have that from, from minus infinity up to 3, and including that, we're going to look at the function 2 minus t. So that function should pass through, let's see, this will be minus 1. Here's my 3. So we can, whoops, sketch this. Whoops, I shouldn't have continued there because I need to move to the piecewise. So let me erase this. So we have that piece, and then I want to draw in the other piece. So now looking at starting at values of t being greater than 3, when I plug in 3 to that t minus 4 function, notice that it passes through that same point. But now we're going to have a positive slope of 1. So this is going to start to look like this. So this is f of t. So the question here is we want to use this to come up with a sketch of the graph of g of x. So before I just jump into the picture, let's think about some key points here that we can find. And of course, it didn't specify a particular interval of x values. So let's just look at, say, 0, 1, 2, 3, 4, and 5. So I'm going to find these values for the function g, and then we can use that to sketch. So just because I can't see it here, when I come down here, g of x I'm looking at is the integral from 0 to x of the function I've graphed above. So to start with, remember that when I replace x with the same number we see in the lower limit of integration, I'm integrating from 0 to 0, I get 0. Now to find g of 1, we're going to interpret that as the area from 0 to 1. So right here. Thinking about that, we can consider here that we could draw maybe about, whoops, I didn't want to highlight that. So we could kind of think about breaking this region up into a square with area 1 plus that 1/2 area triangle. And so together we get 3/2. Then when I find g of 2, I want to find the area from, didn't want to put it in that color, the area from 0 to 2. So we could either tack on that extra triangle area to what we have before, or recognize that that entire triangle is the area we're looking for. And so the base and height are both 2, and 1/2 of that would leave me with 2. So putting that in there, we get 2. When I move to this next part, I want to find now the area from 0 to 3. Notice we're essentially going to subtract now the area we're finding of that extra triangle, and that's going to take us back to 3/2. When I get to the next part, I want to find the area all the way up to 4. So we have another subtraction of a triangle area of 1/2. So that's going to take us back down to 1. And then the last point here would be to find, let's assume that 5 is something like this. Then we're going to have a positive triangle area, and that takes us back to 3/2. So I can sketch the graph of g using these points that I found here. So we see that g of x pretty much is going to go between 0 and 2. So 2 here. We have 0. Put my values here on the x-axis. And so we know that it jumps up to 3/2, up to 2, down to 3/2, down to 1, back at 3/2. And so what we could kind of do is maybe sketch this out, right? Connect these points and continue like that. So this is a sketch of g of x given what we've seen here. And let me see if I can zoom out a little bit. One thing I just want to point out before we move on to the next video is the relationship between the two graphs. If you notice, we'll see here that the function g of x appears to be increasing wherever f is positive, and it's decreasing wherever f is negative. Where we've seen that before is the relationship between a function and its derivative. So it looks like that it's possible that f here represents the derivative of g. And it turns out that that is true, and that's what we're going to see with the second part of the fundamental theorem of calculus.